what we will see now is what is the impulse as the change of momentum. Okay, so now from the second law of Newton, what we have is force is equal to mass times acceleration. So what we have seen in Physics 20 is that force net, which is the vectorial sum of all the forces that the object is experiencing, is equal to mass times acceleration. Now, from kinematics, what we know is that acceleration is the change of the velocity over the change of time. If we multiply by delta t both sides, then what we will have is the force net times the change of time is equal to mass times the change of the velocity. Okay, so now what do we have here is change of time and mass are both scalar quantity and they are both positive. So they do not change the direction of the vectors that you are multiplying it by. Then what we notice is that force net has the same direction as the change of the velocity. Now, this is where a lot of students have a misconception. So it is not the final, necessarily the final. It is not the initial, necessarily the initial direction. Of course, net doesn't have the same velocity as the initial, necessary. It doesn't have the same velocity as final, necessary, but has the same direction as the change of the velocity. Recall what we have said in terms of the change of the velocity. Change of the velocity is delta, like any delta, is final minus initial. So if you have a situation where the initial velocity is, let's say, on this direction, and final velocity is, let's say, on this direction, the change of the velocity graphically will be represented as final. So final velocity. Now, if we were going to add the initial velocity, we would go on the east direction. So this will be the initial velocity. Since what we are doing is we are adding the opposite of the initial velocity, then what we do is we change the direction and save the magnitude. So this will be negative VI. And as you see here, the change of the velocity vectorially is this vector here, which doesn't have the same direction as the initial, doesn't have the same direction as the final velocity, but based on what small transformations that we did, has the same direction as force net. Okay, so now this product of mass times the change of the velocity is known as the change in momentum, because what did we saw as a change as the momentum is mass times velocity, and now when we have a change, we can say that this is the change in momentum or in other words is the impulse. And what did we do from the transformations in terms of the second law of Newton? The change of momentum is equal to the impulse. we can say that the change of momentum is the impulse of an object, or the impulse of an object is the change of momentum that the object is experiencing. Now, in general, the change of momentum and the impulse have the same units, because what we are dealing here in terms of the units is kilograms times meters per second, because even the change of the velocity will have the same units as meters per second. But when we take a look at the impulse, what it is newtons times seconds. So in general, when we talk about the impulse, we say that the units are newtons times seconds. And when we talk about the momentum, we say are kilogram times meters per second. But actually, those are the same units. And I will show you now why they are the same units. So let's suppose that we are starting with impulse. So what do we have is newtons times seconds. From physics 30, we learned that newtons is mass time, or newtons is kilograms times meters per second squared. So if we substitute that, kilograms times meters per second squared times seconds. So this part here is just for newtons, and then we have the seconds that are from the formula. And now seconds and seconds is cancelled out, and then what you are left with is kilograms times meters per second, which are the same units as the units of the momentum or the change of momentum. Now, we in general, what do we say is that when we are referring to momentum, we are stating kilograms times meters per second, and when we are referring to impulse, we are saying is newtons times seconds. Let's see some examples in which we are dealing with impulse and momentum and change of momentum. So now let's suppose that we have an average force net of 12 newtons at north direction, due north, and this force is acting on the object for a period of time of 0.023 seconds. What is the change in momentum? So based on what we said, the change of momentum, which is mass times change of the velocity, is equal to force net times the time. So now what do we have for the average force net is 12 newtons going north times 0.023 seconds. Then in your calculator, 12 times 0.23 will be the change of momentum is 0.28 newtons times seconds going in the north direction. So this is telling us that the change of the velocity, while this force is applied, is is in the direction of north, okay? Because the change of momentum or impulse has the same direction as the change of the velocity. Let's elaborate more into the impulse or change of momentum. So see what we have here. The change of a momentum is, like any change, is P final minus P initial. So when we know what is the P final or P initial vectorially, then we subtract them vectorially. Even if we know them as a value, then we subtract them as a value. So let's suppose that we have a situation like this, vectorially first and then as a value. Let's suppose that we have a P initial that is with a magnitude of 12 newtons times seconds going east, and P final P final is with a magnitude of 25 newtons times seconds going east as well. So vectorially, what the change of momentum will be is P final minus P initial. So what we do is we say P final is this one, okay, at 25 newtons times seconds, and then if we were adding P initial, then we will go in the east direction. Since we are adding negative P initial, then we will add it into the opposite direction. So the change of the momentum will be this one here. This is vectorially. Now let's see mathematically what we will do. So the change of momentum will be P final going east. Is it positive or is it negative? Is it positive? Positive 25 newtons times seconds. Minus, that is from the formula, 12 newtons times seconds going east. Is it positive or is it negative? And it is positive. So then when you use calculator, then you will find that it is positive 13 newtons times seconds, or you can say 13 newtons times seconds going. Positive direction was east direction. Okay. Now let's see a situation when we have a 2D vectors that we are adding, and we will do it graphically and then mathematically. So let's suppose that we have a situation in which the initial momentum is 18 newtons times or kilograms meters per second at 20 degrees north of east, and the final momentum is 15 kilograms meters per second at 30 degrees south of east. So what we are doing is what is the change of momentum that this object is experiencing. Let's first do it graphically and then do it using components. So the change of momentum is final minus initial, and our final is between south and east. So this is P final with an angle of 30 degrees with the east axis, and initial is between north and east, and it is this one here with a 20-degree angle with the east axis. So graphically, what we will see as P final minus P initial will be something like this. P final, so we'll start here. P final is this one. And from the tip of P final, we will add a negative P initial. If we were adding P initial, just P initial, we will go on this direction. Since we are adding negative P initial, then we extend the vector, and then have the same magnitude. So negative P initial is here. Therefore, the change of the velocity will be, or change of momentum will be this one here, which has the same direction as the change of the velocity. Now, when we are doing it mathematically, then what we are doing is we are using the table of components. Now you stop the video here and I will do the components and you can see your work in comparison to my work. This should be the work that you should have in your paper, where you are adding the horizontal and vertical components, and then you are doing all the work that we have been explaining to figure out what is the change of momentum on this case, because when you are working with vectors, it doesn't matter what is the name of the vector, you are working in the same way as we have explained in the first few classes of Physics 30. So we saw how to calculate or how to figure out what is a change of momentum or impulse when we have a vector for final momentum and initial momentum of the object. Now let's see, using the formula, how can we figure out what is the change of momentum when we know the change of the velocity. So this is kind of easy because the change of momentum is the same as saying mass times the change of velocity. And if we have an object with mass of 2.50 kilograms that is experiencing a change of the velocity of 3.80 meters per second at east direction, then the change of momentum or the impulse of this object will be whatever is mass, so 2.50 kilograms times 3.80 meters per second on the east direction, because the change of momentum and the change of velocity have the same direction. So in your calculator, what you will have is the change of momentum is 9.50 kilograms meters per second going in the east direction. So whatever is the direction of the change of the velocity will be the direction of the change of momentum. So this is a second way on which we calculate the change of momentum. Now the third one is when we know either the initial or final or things like this. So if we elaborate more into this formula, then we will see that change of momentum is equal to mass times change of velocity. As we said, even during kinematics, mass change of velocity will be whatever is final minus initial, which if you distribute it, then you will have mass times v final minus mass times v initial, which brings us into this is p final and this is p initial or momentum initial. But now from here, we can find one of the things that we want to find for. So the formula will be if we minus mass times v initial. So let's suppose that we have a situation like this, that the object is experiencing a change of momentum of 2.80 newtons times seconds at, let's say, north direction, straight north. And then the object is with a mass of 1.20 kilograms, and the initial velocity is 3.25 meters per second going east. What is the final velocity? So we'll start with writing down what we have here. What we are looking for, keep in mind, is this term here. Mass times initial velocity, or just the initial velocity, is the same thing. So if we rewrite this, delta P is equal to mass times final velocity minus mass times initial velocity, subtract mass times final velocity in both sides. So what do you have is negative mass times initial velocity is equal to negative mass times final velocity plus change of momentum. And then changing the sign of all of them will be mass times initial velocity is equal to mass times final velocity minus change of momentum. Now, when we do this graphically, what do we have is mass times initial velocity is something going east. Okay, so this is mass times initial velocity. And then what we have for the change of momentum is north. So change of momentum is north, but we want the opposite of change of momentum, so it will be negative delta P. So you see that mass times final velocity is this vector here. And then dividing that with the final velocity, or sorry, mass, we will find what is the final velocity. You do this, stop the video here, and you do this in your own, and I will show you the work on a few seconds. My bad, we are looking for final velocity. So we do know what is the initial velocity. So this will be, the calculations here will be a bit different. So correction here, correction, we will have delta P is equal to mass final velocity minus mass initial velocity. And we do know what is the initial velocity, so we will find what is the final velocity. So add mass times initial velocity in both sides. So mass final velocity will be delta P plus mass times initial velocity. So this configuration here, or vector diagram here, is not quite right. We will do it as delta P that is going north. Okay, so north, and mass times initial velocity, since initial velocity is going east, will have the same direction, mass times initial velocity, giving us the mass times final velocity on this direction. My bad, sorry. So now again, stop the video here, and you will see what is the final work done to figure out what is the final velocity. This should be the work that you have in your paper. And then as the final answer, the final velocity will be 4.64 meters per second at 31.6 degrees north of east. If you do not have this, then again, you have to refer to the video on how to calculate the final or how to work with vectors. So up to now, we saw how can we calculate the change of momentum or the impulse using vectors, just a vectorial diagram, like a vector diagram. of P final and P initial, and then using components when we know what P final and what we know what P initial is, and then we find the horizontal component and vertical component. The other way that we use to find the change of momentum or the impulse is when we know what is mass and final and initial velocity of the object, and then from there we vectorially or using math we figure out what is the change of momentum, and then from there you can even find what is either the final velocity, which was the example that we did in class, or initial velocity. The other way that we can find the change of momentum or the impulse is when we are using graphing. So what did we see in the previous part of this video, or on the beginning of this video, is that the average force net times time is equal to the change of momentum that the object is undergoing to, or the impulse. So that is telling us that if we have a graph that is force versus time, then the area under the graph, so force versus time, the area under the graph will give us the impulse. If we have an area that is like this and time is, let's say, 5.0 seconds, and then we have a positive 20 newtons that this force is the average of this force is, then we can say that this area here is equal to impulse that the object is undergoing to. Now the question will be, what if we have a positive area and a negative area? How do we calculate it? So let's see an example that the average force net is following this graph here. So at T0 it's going into positive, and it is going up to positive 10. And then it is being constant from 3 seconds until 8 seconds. And then it is coming here at 0 at 10 seconds, but then continuing down until, let's say, negative 12 for 12 seconds. And then after that, for up to 15 seconds, it stays at this negative part here. Okay, so now what we are doing is we are calculating the change of momentum from 0 to 16 seconds. Therefore, what we will do is we will calculate the area under the graph. What do we have to keep in mind is that whatever is in the positive will be the positive area, and whatever is in the negative will be a negative area. And when we are adding the two together, we have to consider which one is positive and which one is negative when we are adding the two together to calculate what is the change of impulse. So there you go. We have area 1 that is a triangle that we will calculate as a positive one. Area 2 that is a rectangle, so it is from 3 to 8. Area 3 that is a triangle as well and is positive, so they are all positive areas. While when we move to below the horizontal axis, we have area 4 that is negative and area 5 that is negative as well. Go ahead, stop the video, find the areas, and then add them all together and find the change of momentum for 0 to 15 for this graph of force, average force net versus time. I will show you work as in a few seconds, so stop the video. So this will be the answer. And the way that we are doing it is finding area 1, that is positive 15, area 2, positive 50, and then area 3 is positive 10, area 3 is positive 10, area 4 is negative 12, and area 5 is negative 30, and when you add them all together, 15 plus 50 plus 10 plus minus 12 minus 36, you will have a change of momentum or an impulse of positive 27 newtons times seconds. So this concludes the second part of the impulse and momentum, and I will post some practice questions that you can practice on those type of questions, and then we will deal with any questions that you may have in class.